everyone. Yeah, so for those of you who haven't met me yet, yeah, my name's Gage, and I'm going to be talking about assembly theory and in particular strings. And hopefully by the end of this, I will have convinced you that it is very useful for astrobiology in particular. So in assembly theory, the primary quantity we're concerned with is called assembly index, and it's a complexity measure that corresponds to the minimum number of joining operations that it takes to build an object. So if my object is like X, and I need at least 3 of these steps where I combine 2 things to make something new to get to X from some set of fundamental building blocks, then we say the assembly index of X is 3. And so assembly index is kind of system dependent in much the same way that entropy is, where for entropy I get to choose what my micro and macro states are, and this influences exactly what it means. And for assembly index, these things that we get to choose are what our fundamental building blocks are and what the different joining operations that are allowable are. And so we kind of philosophically, what this thing means is that if I find some really complex object, let's call it A, and it has an assembly index of n, and I find lots of copies of this object, I can be sure that somewhere in the environment there's at least some n construction processes that exist there. So that memory is stored somewhere in the environment that's creating these objects. And that just simply has to be true because for objects even as small as like modest sized proteins, there's not enough like matter on Earth to make all of them in any kind of meaningful abundance. And so this approach kind of lives between 2 different worlds. So one is like, I might want to know the explicit physics or chemistry that's going on and know exactly how these things are actually built every time and understand those pathways. But in assembly theory, we just take what's the minimal like hypothetical thing that we can't rule out as impossible. And this is a massive simplification, so we don't have to understand all the microphysical properties, but we can still put lower bounds on how much it can take to make these objects. And on the other end of the spectrum, it kind of varies from algorithmic information theory, where I would instead say, something is so simple based off of how small of a program I can write that creates it in a computer language. But in assembly theory, we're requiring at every step that everything that's happening is physically possible. And so strings are biologically relevant, as we are all probably quite familiar with. It can be encoded in like 2 different alphabets, so I can write it in like nucleotides or in amino acids. And like many other fields of physics, studying strings is like studying symmetries. And so this is kind of a diagram here of this top string of where different symmetric substrings are within it. And when you look at this, these correspond to meaningful properties in the ways you can build it in the shortest paths. So one feature I want to point out is that, so in this bottom left bit here, I have this 1-2 segment that I'm doubling with itself into 1-2, 1-2. And we call this kind of innovation-like, in that it's like I have the blueprints for it and I don't need to rebuild it from scratch every time. So this has a lot of really nice mathematical properties and it's a really rich subject. So like this thing on the bottom looks like ice cream with sprinkles in it, but it's some kind of weird graph which actually corresponds to like how you reconcile all these symmetries together to calculate like what the shortest build path is, and it has a really nice relation to some like really classic problems in computation theory that tell us about how complicated it is to calculate these things. But much more salient to astrobiology is thinking about what we can call prime strings, or I would argue also materially efficient technosignatures. So the example I want to kind of describe this as is it's just a series of numbers, but what would it mean in maybe a material is if I restrict myself to working with polymer chains, and my alphabet size is basically how many different monomers I have access to. If I want to find how do I efficiently create something that demonstrates I know how to compute a lot of different reactions, then I need something that has as few symmetries in it as possible. And there's actually really explicit ways to construct these things such that they have absolutely no, I can construct, there's many different ways to build these strings, but none of them reuse the exact same reaction twice by virtue of just what they are. And that's a property intrinsic to these objects. And this also kind of highlights the difference between this and algorithmic information theory, because like if I asked anybody to like make the next one, you'd probably all get it right on the first try. There's a lot of regularity in what these objects look like. And so algorithmically, they're not that complicated. But in terms of the physical reactions you need to make them, they really are. So something where I see this going in the future, and that what I'm really excited to do with this is have a dynamics of how life can explore the chemical space of what's possible. And so the picture I want to illustrate, these are not real data, this is just to illustrate a point, is I want to think about some space of objects, and I think a good example is all the proteins that a species creates, say. So we take all of these proteins, and I want to assign distances between them all, and qualitatively, I mean, there's an example of how to do that on the top, but qualitatively what we should think of is the distance between X and Y is the number of joining operations that I need to change to go from one to the other. And so things that are intuitively similar will be closer, as you might expect. And so this is really useful because when we think about what we have as a generative model for like a null hypothesis, like what should life be doing, we know that mutations are things that really only change assembly index by one. Either I'm inserting some large segment that already existed, and so I didn't have to build it from scratch, or I'm making some really small change. And in any case, this is a change in assembly index of just one. And so we have this kind of thick surface of the adjacent possible, like things you can mutate into. And because it's reasonable to imagine that this is happening kind of randomly, we can have some kind of null model for what we expect life to look like. Like what's the shape of this object as it grows in time? And so I like to think of it as kind of spherical, but actually it's probably a little bit noisy just because it is so random. But in reality, I don't think we'll really observe this because some mutations will be selected out and we'll never observe them. And so the way I want to illustrate this is this: you have this kind of noisy sphere on the left, and you have a much noisier version of it on the right. And if I observe this for two different things, the interpretation of this is we're seeing something about like the fitness landscape. Like this is kind of the shadow that makes it through, right? So like there's lots of voids here of things that are either not functional or even hurtful to the system. And by studying like the geometry of these kinds of objects and looking for the ways they scale, we can learn things about the ergodicity of life. Meaning, if I were to restart us from like early Earth times, how similar would I expect the biochemistry to be today that we observe? Just by virtue of how many ways does it seem like there are to actually move in this space? And by extension, we can make inferences about just life in general and how constricted it must be and how diverse will potential alien biochemistries be. So with that, I'll leave you with a fractal that reminds me of the building process, and I'll take any questions.
So how can this be employed to sort of create a criterion for what constitutes abiogenesis based off the assembly complexity?
So there is an excellent Nature Comes paper, I want to say from 2020. Marshall's the first author, where they talk about, so you can do this for molecules, and they find a really big disparity between what kinds of things abiotic sources can produce versus biotic. And this is something that you can measure quite accurately with like mass spec and some other methods too. And so just for a chemical biosignature way, there's a concrete thing that already exists.
Thank you.
Yeah.
Hi, great talk. And I was also just curious, when you're evaluating the assembly theory, is this based off of entirely the sequence, or do you also account for structure?
I don't
like
understand.
Like protein folding or something?
Yes, so this is kind of embedded in like our choice of the definition of the joining operation, right? So like the simplest choice doesn't count the protein folding, but you can imagine that I define the joining operation such that I allow myself to consider those like higher order constructions. And so yeah, it's a choice of your specific instance, yeah.
Hi, yeah, this was very interesting. I'm wondering, how do you consider the starting amino acids you have? Because there's a lot of theories on like what amino acids were like first, or like which evolved later, and like, are you only using the canonical ones that we have in like the current genetic code, or like there any like theoretical amino acid structures that you're exploring?
I'm not. There's someone at your table who does. His name's Thomas. But to relate it to this, I think this is kind of embedded in your choice of like what the fundamental building blocks are. It's like what's your T0? Yeah.
Any other questions for Gage? Okay, let's give him a round of applause.